Okay, we're ready to start for the last part of this event. So now we are going to have the most interesting talk of the event of the week. It's a yearly update. We know this guy. Every time they are talking about how we are going to save the planet. You know, we are already saving the planet, by the way, because we are very efficient with DPDK. We don't waste our resources. But thanks to their work, it will be even more efficient if you have less traffic on your server. So thanks again, and let's listen.
Okay, can you hear me? Oh, I got it.
I'm not.
We're just waiting for the timer.
One
on the slides.
Great, yeah.
Okay, thanks Thomas for introducing the topic. My name is Chris Macnamara. I'm with my colleague whom many of you know, Dave Hunt. We work with Intel. And our journey started a few years ago looking at the efficiency of DPDK and looking to make that green. And we produced a number of different solutions that we're going to go through today quickly and then talk about some of the new stuff, which is the exciting stuff. Okay. I'd like to also credit Reshma Patan, who isn't here today, who also worked on the latest changes. Now, one of the key things that we found out about from our work to date has been kind of a simple question that we asked ourselves, which was how do we know how busy an application is when it's polling 100% of time? And that's a foundational, really, I suppose, intention of an application is that it doesn't really need to be running 100% of the time. But how do we know? If you look at the CPU utilization, you're always going to see 100% because they're always polling. Okay? So we're going to talk about schemes, and Dave is going to talk about those schemes today. And in addition, on the topic of efficiency, we ask ourselves another question. How can we get more out of what we have? So that we do more performance without increasing the energy or the power or the watts, whatever your favorite terminology is of the system. Okay? So we used this diagram a few times in the past. That's right, Dave?
Yeah.
But we want to recap today for those who haven't seen it before. Today there's two fundamental mechanisms. What you see on the right-hand side here is that a bare metal application that's running on the host is using the DPDK APIs directly. That's one deployment model that we see where you can scale up frequency or scale down frequency of per core, depending on the load that you have. And the application can make those decisions itself. When you're in a virtual machine, it's a little bit trickier. Within a virtual machine, you're sitting on a shared platform. You don't really want to have direct control over those, P states or C states. So we implemented a VM Power Manager, which is there today, that implements a scheme that allows the VM to talk to it and tell it what it wants, but also it allows an orchestration or management system to drop a policy on the platform that can be used. For example, during nighttime, during these periods, turn down your power a little bit. Okay? So these mechanisms are kind of summarized in here. And there's a little quiz here. So, today you can turn up or down your frequency to save energy, but what can you do to increase performance? And it wasn't intentional that we left that out. It was. A follow-up from the wine thing. I think this is being recorded. So you can also turn up or turn on Turbo Boost, and there's some of the capabilities that we offer through the libRT Power API. And as I was mentioning, when you're in that virtualized world, the application can send a change frequency command on a VirtIO serial port. So we pass that interface up to the VM so that it can tell the host to turn up or turn down that, and the host can then decide whether to do it or not. Okay? Now, you can also, as I show here, you have change in frequency directly, or you can send a policy that says, go operate in these boundaries. Now, the last element that we have today is, or one of the last elements is that when you don't want the application to have to do any work, how do you tell from the CPU that it's busy or not busy? So we implemented what we have here using CPU counters that can tell you that when you're polling, you enter a very tight loop, which you can see from the CPU branch prediction counter. So the ratio of hits versus misses goes to a very tight loop because you're just running those same few instructions. So you can tell from the hardware that your DPDK PMD has entered a very tight loop. And then you can make a decision on the host without the application knowing to just slow it down a little bit, turn down that frequency, slow down your DPDK thread. It's a dial. Now we stray away from turning off those cores because you don't want to turn somebody off when they don't know about it. You just want to slow them down a bit. So that's available as well. The last piece, as a part of the recap, is, and thanks to John Macnamara who helped us, we've updated the docs and they're on the way onto the main site, but if you want a reference, they're available here for now, okay? Okay, now here's a summary. My God, it looks really big from here.
It's easier reading.
Yeah. But I think, some of the key challenges that we came across was, and you'll see from that, is that there's a feedback loop from the application. It's either telling you, if you're virtualized, go do this for me, or here's the criteria, the policy that you want to go implement. It would be good to see as we move forward, as we saw from the energy discussion this morning from Gavin, about how we could expand the librT Power API to include C states, so that we could have a common way to use that type of capability from an application. And I think we discussed that after. So now, let's get on to the new stuff. We have new telemetry and business metrics that we have made available through a sample app, and we push through onto CollectD. But we have a mechanism that allows the application to report to us how busy it is. And there's many different things you can do with that. If the application is 10%, 20%, whatever, and Dave is going to go through that in just a second. We have looked a lot at prioritization. So how do we get more out of what we have? And this is for scenarios when you have lots of cores and maybe some are busy and some are not busy. How do you unlock those bottlenecks, and how do you squeeze every last performance per watt out of your DPDK application? We're going to talk about those. And the container piece as well.
Yeah, the container piece, we're just mentioning it here on this slide. So we're not going to talk about it later, but that was, remember last year when we put in an enhancement for containers that you could talk to a JSON, it was a Unix domain socket. We could send JSON into that so that VM Power Manager could change the frequencies, and that was aimed at containers, enabling containers to control power. But we found that there was an issue there because there was one FIFO, all containers talking through the one FIFO, they could affect other cores on the system that weren't their own. So we've implemented a FIFO per core, and then we use permissions to clamp down what can access what. So that's just a security improvement around the FIFO interface.
Okay.
Oh, I'm going to talk about this. Okay. So this is talking about determining busyness. So typically, we've got our three, if you look at the center diagrams, at the center of the diagram there, we've got DPDK polling on bare metal, DPDK polling 100% on containers, and again on VMs. So what we want to do, the problem is to try and get a standard mechanism so that those applications can report out to, let's say, orchestration or to CollectD and on somewhere else that how busy it is. So what we've done as a kind of proof of concept is added in an algorithm into L3 Forward Power, and that's implementing an algorithm that sends information to the telemetry library. Now we've increased the telemetry library to send global stats, not just per port stats, but per application stats. And that then goes out through CollectD telemetry up. Now this is a slow reaction, so it would be based on stats collected over time that the orchestration can make decisions on whether to slow down the CPUs or slow down the cores, thereby saving power. And that's in the power saving, the scale down situation. Likewise, there's the other side of the coin is in the scale-up side of things, where again we have DPDK 100% polling in each case, and when that hits overload, say above 80% would be a typical metric used by a lot of providers, that when it gets above 80%, they need to take action. They need to either increase load balancing or kick off turbo or something. So this mechanism gives the ability to do that. There's also the package watts in there. If you notice there's the package watts talking through the turbostat plugin. And again, that gives you, if you're hitting close to TDP, you can either change your load balancing on the platform and so on.
Yeah, I think the thing that is good with this as well is that those patches are upstreamed onto CollectD, which gives us that visibility. And this is, what do you do with that data? What action do you take? And this is looking at overload. So if the applications can provide this busyness indication, you get that visibility that what congestion management or congestion mitigations do you want to make on your platform when you're hitting the thresholds that Dave mentioned. And that's just one use case. The congestion management might be load balance away from that node. It might be, it might be turn up the power, for example.
It might be bring online more VMs on that same system if there's spare cores and so on.
It's kind of two-dimensional because you have a platform view and an application view.
Yeah.
So we think that will be useful when you're polling.
So that telemetry enhancement to the library was released as part of 1908 and is now part of 1908. And what was done there was, as I mentioned earlier, it gives global metrics rather than per port metrics. So when an application then can create, it gives the ability of an application to create metrics that are per application, and they're sent out through CollectD. L3 Forward Power implements it, and also the DPDK Telemetry.py Python script that's in DPDK has been modified. I think it's in the user directory, has been modified so that you can now query per port stats or the global stats. And also there's a new CollectD, as Chris mentioned, there's a new plugin for CollectD that plugs into that Unix domain socket into the telemetry libraries. The way the telemetry library exposes its data is through a Unix domain socket, and it pulls out the metrics and pushes them out from CollectD. So the sequence of events for using this would be, if it's down on the right-hand side, at development, the application implements its own algorithm for busyness, and then it calculates what, between 0 and 100%, how busy it is. So there's a bit of research there to decide in your own unique use case what constitutes 100% busy. And then at runtime, the application populates that metric, and in the L3 Forward Power case, it's busy percent, and empty poles, full poles, and they're implemented in L3 Forward Power. And then the third-party app pulls the metrics, and in this case, we have CollectD and DPDK Telemetry.py. So in order to demonstrate this, we're currently working on a white paper to demonstrate this. So we've come up with this kind of diagram, and we've implemented everything. We've glued together everything in this use case, and we've upstreamed everything required to do this. So we have the CollectD plugin, we have the change to L3 Forward Power, and so on. And we're displaying, we'll see some graphs later on from Grafana. The network load controller is actually Grafana's alert manager that sends alerts right down to T-Rex, and T-Rex then load balances back into the platform, so we can balance between VMs depending on overload. So we're hitting overload situations, and we're increasing traffic onto other VMs, and spreading the load. So we'll see that in a minute. Let me see, was there anything else there? No, that's it. So the white paper's in progress, and that's going to be published soon. So just the last slide on this section is basically, if we take the top right here, we'll see the traffic coming into VM0, the first virtual machine. And as we're increasing 1% every second. So as we increase, we get above 80%, we hit an alert, then that alert comes around the loop and then splits the traffic in two, right? So now we have VM0 and VM1 getting traffic. And that's what we see here. We see the first stream of traffic. When we hit an alert, it actually comes down and comes into two streams. So that's working away happily. And we can see then when the VM hits an alert again, the third VM comes into play, and it starts taking traffic. And the same again for the fourth alert. Then the traffic's shared between 4 streams, and you can see the received bytes for all the VMs is nicely spread across all 4 VMs, so we end up with 4 VMs, or 2 containers and 2 VMs in this case, handling the traffic. So that's a way of using this metric in a real situation to, spread the traffic across multiple VMs. And I think that's about it for that section.
Okay, so as Dave showed those great use cases about how we can override the CPU telemetry and use application direct telemetry to get that visibility into our workloads so that at least we can make informed decisions and understand how busy our platforms really are, our applications are.
There's one more point I'll add to that. Remember the talk Thomas made yesterday about the IDs in the telemetry library. And if we're now given the application the ability to create their own metrics, then maybe we need to reserve some IDs and document. But we'll have to look into that about the faster access to the metrics through IDs rather than names. And that's something we look at after Thomas's comments yesterday.
Yeah, because at the moment we made some names up.
Yeah.
And around the pole counting, so we use as the mechanism we use the number of empty poles that you get in a PMD versus the number that have packets in them, and use that to make a calculation about how busy we are. It seems to be working pretty well. So those are the kind of IDs that or those namings that we need to convert into some, I suppose, I don't want to say, well, it's kind of standard way that we create new telemetry. Okay, so now we know what's going on. How do we squeeze more out of what we have? Okay. There are many opportunities for prioritization and many opportunities for optimization. What we see a lot of is unbalanced workloads, and if you look at NFV, you can see data plane or control plane. You can see where, as we have lots and lots of cores and CPUs these days, how not all the cores are equal. Okay, they're not all doing the same thing from a workload point of view. And we see those kind of unbalanced workloads and the ability to try and unlock system bottlenecks in the software, okay? Now, this applies, as you will well know, to pipeline software architectures where you're, like the HQAS, if you're implementing that across cores, you could have various stages that could benefit from higher performance or higher frequency that would unlock that entire pipeline, okay? Frequency-bound workloads, this is kind of an obvious one, but crypto, HQAS on core, good examples of that. And even when you're in a run to completion, when all your cores are executing the same loop, there may be opportunities to increase the performance of some over others. There may be some that are doing more work based on how you distribute that traffic. There may be SLAs that you would like to give priority from a frequency point of view, which will give you lower latency, okay? We've seen Packet Distributor in DPDK for a long time, and I know Dave has done lots of work with it. That's another good use case where you have a central distributor on your workload, where turning up the frequency can give you a system-level performance throughput because the workers are getting more packets, okay? And another interesting one is PMD consolidation, where you have many PMDs. If you look at virtualized use cases, you might have virtual CPUs that are running RX and TX PMDs. Can you consolidate those onto single physical cores, for example? Okay, how do you pin those onto cores to try and optimize your overall platform? Okay, are there cases where you just have 2 PMDs running on a host and putting them onto one higher frequency core will free up the other cores? So it brings us to the question of prioritization and the benefits of that performance in these types of scenarios. So what we looked at was how do we rebalance the power and frequency to get more out of DPDK workloads? And what you see on this graphic is the blue line is where a CPU will start today. It will come up with a uniform frequency, pick 2.3 gigahertz. And you look at the green line. So we created this mode that allows you to have some cores running at higher frequency, trading off the power within that CPU on the lower cores. So you end up with a 2-tier frequency, which is shown by the green line, and allows you to implement some of those previous use cases for unlocking your system performance. Okay? Now, we also included up at the top, which is, just for completeness, is the turbo frequency. So we have this feature in CPUs today. It's a public feature. It's in Linux kernel as well. It's called speed select base frequency. But we look at this as a way to get more out of our workloads and more out of DPDK, with a goal to solving some of those issues that we talked about, or some of those opportunities is probably a better way to put it, that we talked about in the previous.
Within the same TDP.
Yes.
Yeah.
So that's where the power twist comes in, as Dave is saying. is
Balances.
that we've kind of rebalanced the power and frequency to achieve this. Okay? Now, the code wasn't a huge amount of change to make this happen, which was kind of nice. But if you look at the core capabilities, today we have the ability through the RT Power core capabilities to, as you'll see there, it's reporting that you have turbo available, which is a CPU frequency increase. And we've added the ability to find priority cores, which are higher frequency cores. Okay? And this brings us to asymmetric core frequencies or heterogeneous core frequencies that we can find and then attach our key threads to as an application developer. And as you see on the right-hand side here, the application will query, just to give you an idea of the flow, application will query the capabilities of each available core, and then it will pin the cores there, or the threads, the workload's high priority cores, and the application will run as normal. And we have sample code for this in L3 forward power. This sits on some of the kernel infrastructure that I mentioned earlier, and you can look at pulls this from the kernel sysfs base underscore frequency field. Do you want to add anything?
No, that was it. I was just going to mention the base frequency.
Okay.
Yeah.
Okay. So one of the interesting pieces that I think I'll tell the story about this. So myself and Dave had a discussion about the ability to be able to start DPDK on the CPU where you wanted it. Okay, so we were having a big debate that you could.
Without changing the application.
Without changing the application.
Just you launch it as is.
So this was the last day in the office of 2018. So everybody wanted to go home. But what we wanted to do was launch the application where we wanted it. So assuming all the cores have this higher standard frequency available, we want to be able to put threads onto the high tier or the standard tier of frequency. And as we debated this for much time, after having a look in the documents showed us that you could do this. And we kind of thought it was going to be a challenge for us to do this, but just to highlight this feature,
it's already there in the EAL.
It's already there in the EAL.
Yeah.
So you can launch your application today with using the EAL. It will just go cores 1 to 12. It just launches them in order. With this, you have the ability to say I want thread 1 on core 3 and so on and so forth. So this was great because we weren't aware of it, and it was hidden to us anyway, and we wanted to highlight that as we move forward into scenarios where you want to put and organize your threads a bit better when you launch. This is a great feature.
Yeah. So we specifically wanted, like we were given it 4 cores or 6 cores or whatever, we specifically wanted the second or third core to be pinned to the high priority. So yeah, this nicely solved that problem.
Yeah, so in the environment now where you have differentiated core frequencies, you have the ability for your application to go in and find them and go use them, or you have the ability to just launch your application onto those cores, which gives us a lot of flexibility. So the application doesn't need to change to be deployed on this. Okay, so that is the end of the presentation. We have a few minutes for questions, and I'd like to acknowledge the team that you see here, and also the Collect D community who helped us with the DPDK telemetry plugin and turbostat updates. So thank you. We'll take a few questions. It's kind of hard to see.
Peru.
If I set some cores as priority cores at runtime, is there any ramp-up time before the frequency practically changes? or does the change happen immediately?
It's in terms of microseconds. The change will take probably somewhere in a range of 500.
That's it. That's if you're changing the frequency. But if you're using SSTBF and you query the high priority cores, they're already at that frequency. So you're just pinning onto that higher core, which is already running at, say, 2.7. And you're pinning your low priority to the 2.1 cores, for example. So when you pin them on those cores, they're going to be running at 2.7.
Yeah, so it's a good point because you can configure this after boot, and the kind of common model we hear of is that you will configure the CPU with 2 tiers and then drop your workloads in there versus, deploying your workloads and then trying to manage it post, but it depends.
And it's worth mentioning that Kubernetes, OpenStack, there's work ongoing there to make this.
Yeah, it's there. It's public in both those.
Yeah. So they're aware of, they can query which cores are high priority because that comes out of the BIOS. That's a fixed, you don't configure which are a high priority core. It's out of the box, skewed into the particular CPU you buy. And particular cores will have high priority, and you have to query that to see which ones are high, which is through base frequency and sysfs. And orchestration is being made aware of how to, or which cores are high, so you can deploy your workloads onto those.
Okay.
Anybody else? Question from Jen there.
Yeah, so Dave, Chris, so when you talk about the business, you will do the check using collectly and using, so how many cores you are using to check the business?
The busyness is part of the application itself. So when the application is running, it's counting, well, in the example that we have in L3 Forward Power, it's the poll loop that's actually counting the packets, and it's calculating the business in that poll loop. So it calculates empty polls, full polls, and it uses, then I think in this case, it's actually using how many polls it gets over a particular amount of time.
Yes, exactly. Yeah.
And it fills out that metric. So it's the main thread that's actually doing the update to the metric.
So it's inside of the user application?
Yes, in that case.
How about, have you tried, this is user case and we run it separate for the
we could. There's remember last year we talked about the branch ratio calculation. That could report, but it wouldn't be per application. It would be per core. So in this case, if you have 3 or 4 cores running on an application, the application can gather all how busy each core is and then produce one busyness number for the whole application. Whereas if you're doing it out of band, that out-of-band mechanism would need to know how many cores are running on each, or how many cores each application is using, so it's a little more tricky.
Yeah, so does it hurt performance? When you do the track inside of the user application?
We
haven't seen any degradation. It should be
there is a
minimal
cost,
cycles.
but it's minimal, we believe. Yeah.
Yeah, you're literally
it's 2 stats at the moment. So.
Yeah, you're incrementing a counter, so it's not going to be a huge amount.
Okay, thank you.
Okay. One more.
So I understand that business is up to the application, and I understand the reason why. Do you have any best practices or range of examples of good ways to do this? I heard one example, the number of pulse that comes with packets or without packets. Do you have more other examples?
We just pushed that one into the Power Sample app. There are a couple of others. We count packet arrival rate. So we try to calculate the, say, gigabits per second within the application. So you would take the interface, say 10 gig. The worst case packet arrival rate would be you'd get a 64-byte packet every 67 nanoseconds. So we try to calculate the rate at what we're receiving, and that's available as a sample app as well. It's in a sample app as well, but I don't think it's quite what you're looking for.
I'm looking for the per L-core business?
Yeah.
We found, I think, the best one we found so far would be the PMU counters, the branch ratio. That's worked out quite well. And we've heard from other people, other external people who've been researching this same nut. It's a hard nut to crack. And they came to the same conclusion that our branch ratio is quite a good metric for using branch hits versus branch misses. So when you're in, as Chris explained earlier, when you're in a tight loop, it's very low. But as soon as you branch out to all the other code that you have to execute to actually receive and process a packet, your ratio increases dramatically. So that's quite a good way of doing per core. And with that method, you don't even need to change the application. You're just looking at the PMU counters. Now, there is a hit of reading the counter off all the CPUs, but that's of the order of, I don't know, it's minimal.
I'm asking because we're using it for two purposes. One purpose is power management. No need to go use more power than we need to. And the other reason is there are some MIPS that show where you show your per CPU usage between 0 and 100%. And I would like to show a number that reflects reality and not a number that's like a Windows completion graph that stops and then suddenly
90
all the way, and then the last 90% of the time take the last 1%.
Yeah.
So kind of a more linear value.
See, there is, and I hate to admit it, but there is still a limitation to the branch, even the branch ratio app, because you have to know for your particular application on that core what constitutes the ratio when it's at 100%.
Yeah, so what? There's two things here. There's in the application calculating the business, and Dave is saying if you don't have anything in the application, you can look at the CPU counters, and they'll tell you, like we were saying, if you're idle or busy, how busy you are is the question, and how you can, there's a line there of performance of what your branch ratio looks like when you get to say 50% busy. But what we're saying is that you have to do some work to figure out where that number is, rather today where we don't have something automatic. Whereas today you can look at the counters and say, you're idle or busy. How busy? You have to kind of figure that out a little bit yourself.
That's the next nut to crack.
Yeah, that's what he's saying.
Yeah.
Okay, thanks.
Okay.
Questions? Thanks.
Okay, thank you.
Let's stay on time. We have.
Thank you.
Sure.
Yeah,
Thanks.
30 minutes. Yeah, great.
So the next talk will be from Harry, and it's